Hello everyone. Our group is presenting on learning frameworks for various airfoils. Our group members are Gabriel Atcher, Yash Chitale, Yubin Kim, and Akib Syed. My name is Akib Syed and I will be presenting this work. The motivation is as follows. Aerodynamic parameter optimization is instrumental to the design of aircraft components such as wings, propellers, and rotor blades. Our optimization framework is comprised of assessing performance metrics given various airfoil shapes. The objective of the present work is to assess aerodynamic performances of airfoils while minimizing the corresponding computation time for said analyses. We implement PARSEC parametrization, which transforms airfoil coordinates into 11 parameters, thereby curtailing computation time. Additionally, we curtail the number of parameters to 9 by virtue of neglecting the trailing edge thickness and the trailing edge coordinate, as these are not of importance in actual scenarios. For our work, we are given the flow parameters such as the Reynolds number, the free stream Mach number, the angle of attack, and the airfoil shape. The objective of the research endeavor is to leverage machine learning frameworks to obtain estimates of aerodynamic performances for any airfoil. To do so, we do the following. We first collect a data set and perform data preprocessing. Following this, we implement a clustering algorithm to identify relevant clusters in the data and create classes to predict. Following this, we implement a classification framework to predict to what class, which was created earlier in step 2, an airfoil belongs to. We obtain the dataset from the UIUC airfoil database. This database consists of data for approximately 1,500 airfoils, and we obtain the dataset for our purposes in a .dat file format. Following this, we process the data by running the airfoil data obtained earlier through xfoil for our aforementioned flight conditions, and also extract the PARSEC parameters simultaneously. We first implement GMM clustering. The airfoils were clustered mainly based on their CL values, that is, their lift coefficient values. The GMM also identifies most of the symmetric airfoils and places them within a separate cluster. The best value for the silhouette coefficient is obtained using merely 2 clusters, after which there is a significant drop. The next best value is obtained at 7 clusters. The Davis-Bolden index portrays a similar trend. We determine 6 clusters to be the optimal amount. Additionally, we note that it is difficult to determine the lift coefficient, drag coefficient, and volume ranges for our airfoils based on clusters alone. Next, we leverage k-means using the aforementioned optimal number of clusters. K-means is an unsupervised learning algorithm which clusters the data into a k, in this case k equals 6, number of distinct partitions. Following this, we implement expectation maximization. This entails arbitrarily selecting clusters, assigning labels based on clusters of closest proximity, and subsequently determining new clusters until we attain convergence. This approach can categorize airfoils with 0 lift coefficients into a single group. Afterwards, we leverage spectral clustering, which utilizes nearest neighbor graphs to cluster unorganized data into groups based on common features, using the aforementioned optimal number of clusters, 6 in this case. We present 2 models for our neural networks. The first of these models is comprised of 5 dense hidden layers. The first model is composed of fewer hidden layers, but each layer consists of more neurons in each hidden layer. In contrast, the second model has more hidden layers, but with fewer layers within each hidden layer. We plot the accuracy versus the epochs for the first model. From the graph, it is evident that we have low accuracy and overfitting. The low accuracy is a consequence of a lack of data points and the lack of visible separation in the k-means clustering. Following this, we present the second model. In this case, we implement regularization to prevent overfitting with a regularization constant of 1.75 times 10 to the negative 3. The accuracy improves a sufficient amount, attaining a value of 65% for the validation data. To summarize, we leverage a 2-step approach. First, we clustered the data to create labels for classification. Following this, we classified the airfoils into 6 clusters. The objective of the research endeavor was to determine an estimate of the aerodynamic parameters for the airfoils given their initial shapes. We additionally conclude that neural networks significantly expedite computation time relative to CFD techniques. However, the limitations of our approach arise from the classification of the airfoil into 6 broad clusters, which yields results that are not as accurate as those obtained using CFD. Future work will address this, in that it will focus on refining the categories and tuning the model to mitigate the issues associated with the aforementioned low accuracies. That is all. Thank you for your time, and I hope you have enjoyed our presentation.